Hey, calculus, if you take your notes out, we're going to look at parent functions and transformations. The first thing I'm going to do is run through some of the parent functions that we'll see, not all of them, and then look at transformations, how they get moved up, down, left, and right, and then some problems where we, given a function, see if we can write it, or given the function, see if we can graph it, um, and that'll be it. All right, so hopefully you guys have this on paper because I don't want you to have to copy this down. If you have the function f of x equals some constant, that's just going to be a horizontal line at whatever c is. So I don't know what c is. Let's call this c. Then we're going to have a horizontal line at that point. So if it was like the line fx equals 2, which is a flat line at 2, you can plug anything you want in here. No matter what you plug in, your output's going to be c. So the domain is going to be all real numbers. And that's the symbol for real numbers. If you guys want, you can write negative infinity to infinity. It's fine. The range is only one output to this function, that's c. So the range is the y equals c. F of x equals x. This is a linear function with a slope of 1 and a y-intercept of 0. You can pick 1x plus 0 if you want to think back to mx plus b. But this is also called the identity function. If you input a 1, you output a 1. If you input a 2, you output a 2. So it's going to look like this, and I'm just going to connect it with a line. So that's the parent linear function. You can plug anything into it, you get that same number out. So the domain is going to be all real numbers, and you could say negative infinity to infinity. The range is going to be the same thing. I can get anything, I can put anything I want to this function, and whatever I put in, I get out, so I can get out anything. So the domain is also going to be all real numbers, or negative infinity to infinity. The quadratic parent function is x squared, and that's just that U-shaped parabola. I know where the points would go, but I'm not worried that you guys have it right on the money. So you can plug any number in and square, and squaring doesn't break your calculator. So the domain is going to be all real numbers, or negative infinity to infinity. The range, though, is not all real numbers. The only outputs to this particular function is going to be numbers 0 or bigger. You'll never get a negative number because when you square it, it always becomes positive. So we're going to include 0, so we use the bracket, to infinity. The cubic function, that's f of x equals x cubed. So that one looks like that. Here you can cube any number without breaking a calculator, so the domain is going to be all real numbers. The range, again, you can get positive and negative numbers here with all the decimals in between, so it's also going to be all real numbers. When I say break the calculator, like if you divide by 0, your calculator will say error. Whatever you plugged into that function was not in the domain. So dividing by 0, squaring negative numbers, natural logging, I think number 0 or less will give you an error. So with a cubic function, you have to worry about that. The square function you will. So the square root of x is going to look like this. It's not that much different from the x squared function. Just kind of like tilted or rotated 90 degrees, and you only got half of that u. So I can only plug positive numbers into here. I can't plug negative numbers in, or I'll square root of negative number will give me an imaginary number. So the domain is going to be all numbers 0 or bigger. And the range is going to be the same thing. I can only get positive numbers out of this. I can get all of them because I can go to infinity, but I can't get any numbers below 0. And this probably looks a little bit familiar to some of you. Maybe not all these functions, but hopefully some of them. The 1 over x function, I'm going to call the reciprocal function. That one is a rational function where we get some asymptotes. Like that. So the domain here, you can divide 1 by any number except 0. So it's going to be, so I'm going to write all real numbers except the set containing 0. Yep. The range, I can get any number, 1 divided by 5, 6, 7. I can get any number as an output except 0. There's no number I can divide 1 by to get 0. So there's no 1 divided by something equals 0. It doesn't happen. If I use a really, really small number, 1 divided by a small number will get me really, really high numbers, but I'll never get 0. So it's going to be all real numbers minus 0. I'll be honest, I'm not happy about the way I just explained that, but we can talk about it in class more later. And that function is going to come up a lot. We're going to deal with rational functions. Plenty. All right, absolute value function, that's the absolute value of x. That's the V-shaped graph. When you have positive inputs, it's just going to look like y equals x. When you have negative inputs, instead of being down here, it's going to be flipped above the x-axis and maintain those positive values. So you can take any number you want and make it positive. Whether it's positive or negative, that's fine. So the domain is going to be all real numbers. The range, though, you're only going to get positive numbers out of this. So you can get 0 or bigger. So 0 to infinity. I realize I'm going fast, so I don't know. Have someone click into pause the video so you guys can jot these down. All right. So those were some parent functions. Now let's see how we can move them around the grid. Suppose I had my function and I'm adding some constant to it. That's going to shift it up whatever that number is units. So if I took the square root function and I added 2 to it, instead of being right here, every point is going to go up 2 units. Okay. So I'm going to erase that. So that is what that's going to look like. If you subtract them, it's just going to go down. So vertical, shift, down, C, units. So if I did the square root of x minus 1, if this is the square root of x, I know it's not the best of it, it's just going to go down 1. And so it'll look like this. So that's how you move things up and down. When you're adding a value inside of the function, that's going to be a horizontal shift. Some people use the word translation. I'll just throw that in now. Same thing as a shift. And that's actually going to go to the left C units. When it's inside the function, it's like the opposite of what you would think. Because you think positive go right. To convince yourself, if you ever make a table and start plotting points, like x and y, if you just look at like -2, -1, 0, 1, 2, you'll see kind of why this works out. So if I did the square root of x plus 2, that's going to move my function to the left 2 units. So it's going to still be that same square root function, just to the left. And f of x minus c, that's going to go to the right. So we have another horizontal translation. And that's going to go right C units. So this one's going to go to the right. I think Beyonce has a song about that. F of x equals the square root of x minus, let's go -3, change things up. So this one's going to go to the right 3, 1, 2, 3. And it looks something like that. All right, so translations going up and down, left and right are pretty nice. When you have a negative outside of your function, that's just going to be a reflection. When it's outside of the function, it's reflection over the x-axis. So if I took f of x to be the negative square root of x, instead of being above the x-axis, we're going to flip down underneath it. Okay. When the negative is inside the function, so if I had something like the square root of negative x, if you're guessing, you might guess it's a reflection over the y-axis. So instead of being like this, we're now going to shift and be over here. Okay. If you're multiplying by a constant that's bigger than 1, so if I had something like 2 times the square root of x, actually, well, yeah. I do want to talk about specifically 10 times the square root of x. and I'm not going to talk about it in the video, but if you guys remind me, I have a little story about that one. But if I do 2 times the square root of x, that's going to be a vertical stretch. It's just going to double the height of all your points. So if my points were going to be here, instead of being 1, it's going to be twice as high. Instead of being 2, it's going to be 4. And it's just going to stretch it up. It just doubles everything. If you use a number smaller than 1, like a half, now things are going to get half as big. We'll call that a vertical compression. And so something like 1/2 of the square root of x. Now the points are going to get like smushed. They're going to be half the height that they were. Okay. All right, so let's jump down to the notes here. I'm going to skip these guys for now. Don't worry about them. So these are some examples that you guys are going to have to do on your own for like homework and stuff and on the quiz. So recognizing the parent function, what's the domain range, graph the transformations, and identify the transformations given the graph. Let's skip that guy for now. So I'm not sure if this is printed out in your notes, but if not, write these down. The order to follow when graphing. This is a good rule of thumb. There might be situations where these 4 steps in order may not produce you the exact graph, but I'm not going to give you crazy ones. The purpose of being able to graph these functions is so you can quickly sketch an easy graph. If there's a graph that's nasty, you're just going to plug in your calculator or Desmos or something. So this is just kind of like, I don't know, if you're on the streets and somebody gives you an easy function to graph, you can kind of do it quickly. When it gets complicated, just use graphic calculator or Desmos. But we're going to do horizontal translations first, then we'll do our dilations, then our reflections, and then our vertical translations. So we'll do our left and right first, up and down last, remember that, and then your scaling and your reflecting in the middle. All right. So first example, if it's not written right, but we have x plus 2 squared minus 3. The parent function here is x squared. So I know that's going to look like a parabola. Now the horizontal translation of plus 2, that's going to be 2 units to the right, psych to the left. So now it's going to come, and I'm going to use a dotted line. So this is the original parent function. And then we're going to go to the right 2. Let's just do it in this color, I guess. And then the minus 3 means bring it down 3. So down 3 units. So then, I don't know, we'll go back to blue. 1, 2, 3. So this is the final product. Okay. So move 2 to the right, 2 to the left, 3 units down. Remember, plus goes in the opposite direction that you'd think. And that's it. Check it on Desmos if you want. Now we're given an absolute value, so the parent function here is going to be y equals the absolute value of x, which is that v-shaped function that we just looked at. Okay, so let's go left and right first. We're going to go 3 units to the right, because of that minus 3. There's no dilation here. I'm not multiplying this by 4 or 5 or a half or anything like that. But there is a reflection. This negative sign is outside of the absolute value, so that's going to be reflection over the x-axis. And then the plus 1 is just going to go up 1. So 3 units to the right, 1, 2, to the right, 1, 2, 3. And then we're going to reflect over the x-axis, and that's going to be downward, upside down v, and then up 1, so it's going to bring it up here. So downward facing v. So the vertex is, what was that, 1, 2, 3. Vertex is 3, 1. All right, so that one had a reflection in it, not too bad. Okay, so now we got a couple things here. We have another parent function, that's the square root function. So left and right first. The plus 3 means it's going to go left 3. The dilations is times 2, so it's going to be, what do I call that, a vertical stretch, I believe. The factor's 2. The negative outside of the square root is going to be reflection over the x-axis. And the plus 1 is going to go up 1. So square root function looks like this. So we're going to go left 3, 1, 2, 3. We're going to scale it up. So I'm going to use a different color for this. It's going to be stretched higher. We're going to reflect over the x-axis, and now it's looking down. And then up 1. So my final product, I'm just going to go up 1. It's going to be something like this. Okay. And there it is. I just remember when I was taught this, the teacher kind of just did one transformation at a time, and that's, I don't know, it hit right for me, so that's how I do it. But you can do it a lot of it in your head and go for it. All right. This one's a nasty little bugger, and I probably won't give you one like this on an assessment, but let's see if we can follow our steps here. The parent function is y equals x cubed. So left horizontal first. We're going plus 1, so that's going to go to the left one. The minus inside the function is going to make me reflect over the y-axis. And the minus 2 is going to make me go down 2. So let's see here. The cubic function looks something like that. I'm going to move it left 1, so then it's going to come over here. And then we're going to reflect over the y-axis. So I'm going to erase this one and be careful here. So this is the y-axis. Let's make that nice. So what that's going to look like is, let's see, it's going to come down kind of like that was. This point's going to get reflected over here, so I'll do this again. And then we're going to come down. So what people will do here, and this is what's incorrect, is they'll look at this piece, and when they say reflect it, they'll do this. That's not reflecting over the x-axis, the y-axis. That's reflecting over the line y equals -1. That'll be reflecting over this line, which is not correct. So just be careful with that one. There's our reflection over that. All right, and now go down 2. So here's my vertex, or it's actually called a point of inflection. It goes down 2. So I'm going to make this a dotted line or a dotted curve. And now that is what we should be working with. All right. Again, the purpose of this is I'm going to be very often talking about graphs like, negative x squared plus 4. And very quickly, the y-intercept's 4, it goes up 4, it's going to open up downward. So I just know right away it's going to look like that. You can do a little algebra to know that the zeros are going to be -2 and 2. But that's going to help because there's going to be questions. It's there's going to be questions where the shape of this is going to matter. It doesn't really matter what we're going to use it for because we'll get there when we get there. But it just saves you a lot of time. You can see the graph without having to go look it up. Skip that guy. All right. Each of these, we're going to tell me what the parent function is, describe the transformations, and write the equation. So the parent function is going to be the square root function. Excuse me, the quadratic. So that's going to be x squared. The transformation, so it went left 2, up 1. left 2, up 1. And let's graph that, or let's write that down. So it's going to be, the plus 1 is because it's going up 1. Now it's going left 2, so it's really going to be x plus 2, not x minus 2. Remember, it's the opposite you would think. Okay, so here we have the cubic. So that's f of x or y equals x cubed. It looks like it's going right 2 and down 1, 2, 3, 4. So the down 4 is going to be minus 4 at the end, and the right 2 is going to make it x minus 2 in the parentheses. It's the opposite you would think. Oh, crap. That was, I just did letter C. So letter B would have been right 2 down 4. So, oops. That's part C and that's part B. All right, here we have the square root function. So y equals the square root of x as the parent. Right, it looks like it's going right 1, and then it's reflected the x-axis. So we're going to have f of x, let's see, it's going to be the square root. It's going right 1, so it's going to be x minus 1. And then it's reflected over the x-axis, so we're going to tag a negative on it at the outside of the function. Okay. I think that's it. All right. I know this one kind of quick, or I rushed through it. We can talk about it more in the next class, but there's going to be some practice problems for you to do. Hopefully you guys have a printout. If not, if you remember how to access OneNote, the homework for that, for what we just did is right here. And if you're in OneNote, it's kind of too late now, I guess, if you already saw the video. But on your own, you could double-click these PDFs, and a printable version of this will come out that prints it out nice and cleanly. So there's 3 different PDFs here. There's the parent functions, the transformations, and then kind of the notes. Anyways, that's it, guys. Hope I'll see you guys soon. Take care. Bye.